Okay, good evening, everyone, and welcome to this ICTS distinguished lecture as part of this cosmology program. I thought I would also take the opportunity, in addition to thanking our distinguished lecturer today, Professor Nick Kaiser, I would also take the opportunity to introduce ICTS a bit to many of you who were probably not here last week in the school part of the meeting. Since many of you arrived this week, I'll just walk you through a few minutes of what ICTS is. But before that, about the ICTS Distinguished Lecture, we have a tradition of having eminent scientists giving, as part of our program, within the presence of many of the other experts, a lecture which makes their science accessible to a broader audience. And so at a scientific colloquium level, so that is been the tradition of the ICTS Distinguished Lecture. And we've had a very long list of eminent people, which you can see on our webpage. Some of these, all the lectures are archived on our YouTube channel, so you can watch some of these excellent lectures in the past. And I'm very happy that in this program we have Professor Kaiser give this. So ICTS is a center of the Tata Institute of Fundamental Research. This is a visual glimpse of the institute from the top of that big tower. It's a water tower. From the top of that tower, you can get an aerial glimpse, so to say, of ICTS. Though this was taken a bit before, it's much, I think the trees have grown much more by now. We are in this auditorium here, and this is the sort of the seminar complex of ICTS. This is the academic block where our faculty, students, and other researchers sit. It also has the library building, which I invite you to visit. It's a very unusual and very nice place to actually sit and think big thoughts. The guest house, the cafeteria, and so on. It's a small campus. You've probably gotten a sense of it by now, but that's not what I wanted to tell you. I wanted to tell you a little bit about what we are as a scientific institution. In a way, so we, like all the centers of Tata Institute of Fundamental Research, which is now a very distributed entity from in Bombay, Hyderabad, Pune, and Bangalore. We are one of the newest centers of TIFR. Each center has a unique mandate, and ours is to sort of combine with our research high quality programs like this, in some ways patterned on the KITP or the Newton Institute or the Galileo Institute and so on. Our mandate is broader than some of these physics institutes in that we have programs in physics, mathematics, computer science, quantitative biology, and even climate sciences more recently. So I'll say a little bit about each of them. By the way, this was something that one of our previous participants was inspired to paint of the library. So I put it up there that in case there's any of you are struck with inspiration and come up with something, please share it with us and we'll be very happy to highlight it. This is a collage of our researchers. Our researchers are in, we have about 30 faculty. We have people in various areas in the mathematical and physical sciences. They're not structured in departments. They are in somewhat fluid groupings, and people talk a lot across these groupings. We have an active PhD program, which has nearly 80 students, and also a postdoctoral program with a good number of postdocs at any given time. In the mathematical sciences, some of the areas at ICTS are in dynamical systems, PDEs, climate sciences, in geometry and mathematical physics, probability theory, and most recently in theoretical computer science. In the physical sciences, we have astrophysics, which has not only more conventional astrophysics, but also an active group in gravitational wave research. Complex systems sort of encompasses quantum many-body systems, condensed matter physics, in statistical mechanics, and also fluid dynamics and quantitative biology. And finally, string theory, quantum field theory, and quantum gravity. These are posters from some of our programs. Our programs, and this is one of the central messages in my talk to all of you, is that they are organized by the global scientific community. So we invite proposals from people from across the world, scientific institutions, anywhere. And it's based on an open program proposal submission system. Twice a year, there's a call. So it ends, the next one ends in the end of June, so middle of the year and end of the year, so it's easy to remember. The 6-month calls, the 6-month periods, you can submit proposals for programs roughly a year and a half in advance. So currently the call is for programs to be held from October 2024 to March 2025. So you should plan in advance if you want to organize a program here, at least for programs like this one, which are 2 to 3 weeks long, which is sort of a standard program size. They often have a pedagogical component, and the school part of this meeting is one such. But we have a variety of formats, but we definitely would like to see something for younger researchers, for students, postdocs, and so on. We also have about 1 week long discussion meetings, which are much more intense, sort of focused on collaborations, etc. There are actually now close to 35 per year programs. After the pandemic, I think people have gotten back to these things with a revenge. So we have a very packed schedule, and we have over 2,000 people, and about a third of that from outside the country. I think it's fair to say that in our 7 or 8 years of existence, we've become a sort of a science hub for the country's researchers and an interface to the world. And a lot of new collaborations, ideas have come out of the meetings here. We've started keeping count from the last 5 years, and we encourage people who have ideas that this meeting contributes to, and if they lead to publications, please acknowledge ICTS. The program office will have a standard sort of acknowledgement sentence, and that enables us to keep track. And of course, as you know, it helps with the funding and to make the case why these are worthwhile institutions. And the other thing, the concrete outcome from these programs are the talks, which we archive. And there are now over 7,000 talks on our YouTube channel, and been very popular with, I think, over 50,000 subscribers currently. So people signed up for receiving updates on these, on our programs. We have a number of special lectures, which are also part of this, part of our YouTube channel. Last week, we had Joe Silk give some of the Chandrasekhar lectures and the distinguished lectures here that we're having now, and a number of others, which you can check out again on our YouTube channel. Finally, about the last component, which we also take very seriously, is outreach. Including, so this includes science communication of a more standard kind, involving public lectures, which we hold at the planetarium, the Copy with Curiosity series. There's something online called Vigyan Adda for undergraduate students, public lectures, etc. And once again, the talks are live streamed, and so people join in from across the country, from other parts of the world as well. But we've also tried to have a few interactive exhibits, and we started something in the pandemic called Cosmic Zoom, which is sort of exploring the cosmos in powers of 10, so to say, across various scales. And at each scale, I think people can sort of go and discover new things on their own in terms of material, talks, etc. We've also been active in terms of science pedagogy. demonstrations in schools of scientific principles, training for some of the science teachers of the state, and very recently a math circle network jointly with the Raman Research Institute to an in-person math circle network to identify, nurture talent in mathematics for children in grades 6 to 10, and an online math circle, which we do in partnership with a lot of other institutions around the country. So this is just to give you a little glimpse of what ICTS is. I hope you'll have a very productive stay. Probably lots of papers, hopefully, will come out of it, and ideas at least. And I hope to see many of you back here for many of our future meetings as well. Thank you. And now I invite, I think, Shubha, who will first introduce the speaker and carry on with the proceedings.
Okay, so it's really a real pleasure to introduce Nick Kaiser to all of you over here. Although for most of you, he doesn't need an introduction. This is quite evident. If you go walk around the institute, you will see Kaiser written randomly in many of the green boards. So students who have been here last week during school have already been introduced to a number of things and concepts that Nick gave to cosmology, like how to do cosmology with big lensing, the Kaiser effect or the redshift space distortion, people talking about bias in halos, people who had this power spectrum estimation, the FPK, all of these things sort of started with Nick introducing the concept in cosmology. However, for the sake of completeness, let me just say a little more. So Nick did his PhD in Cambridge, working with Martin Rees in 1982. And then after 5 years of postdocs in different places like Berkeley, Santa Barbara, Brighton, and Cambridge, then he became a faculty in CETA, Toronto in 1987. But he was there only for 10 years when he decided it doesn't want to be in that cold Toronto winter and wanted something completely different, where there's a lot of sun, so he moved to Hawaii. So he was at the University of Hawaii for 20 years. And then finally, 5 years back, he went to ENS Paris. During the period in Hawaii, of course, he was initiated and was a PI of the Pan-STIR survey. Now, as I mentioned from the beginning, Nick has done initiated many fields in cosmology, and for that he has many awards, but I'm not going to list all of them at all. He was a fellow of the Royal Society, but a few years back he got the gold medal of the Royal Society for his lifetime achievement, and also the Gruber Prize in Cosmology. Now, many people, and there are others who have won the gold medal and Gruber Prize, but I don't think no one has an asteroid named after him. So Nick is unique in that sense. And with that note, I will ask Rajaram to hand over a small token to Nick.
Well, thank you both for the introduction and for the gift, whatever it is. It's certainly a great honor and a great pleasure to be here. I'm very nervous, following in the footsteps of all the other truly distinguished people. But it's been worth it for me because not only getting to see lots of old friends, seeing particularly the young people giving their presentations on Monday, what they managed to accomplish in just a single week at this workshop was truly a pleasure. And I hope they don't blame me too much for having tortured them with the Kaiser formula and stuff. Anyway, it was a bit tricky to think about exactly what to give for this talk, because there's many of my colleagues who are experts in lensing and all parts of cosmology, and then there's all the people with broader who aren't interested in that so much. So I thought I'd talk about something to do with lensing, which probably forms, it's a large fraction of what we've been talking about at this meeting. The meeting's big data cosmology. And here are some of the toys which are going to be used for the lensing side of this, well, and more generally. And we've got the Euclid, which is going to be launched this summer, LSST, which is going ahead and on a longer time scale, the square kilometer array, and that's what's going to generate the petabytes, whatever, you know, I forget what comes after petabytes of data that we're dealing with. But what I thought I'd talk about in this talk is, how did we get here? Like, you know, how did we convince governments to cough up a billion euros a piece for these kind of toys? And the other thing that's amazing is it's not just the technology, it's the social engineering that goes with this. Each one of these has a collaboration, you know, of upwards of 1,000 scientists and engineers working together. It makes me think of building the pyramids or cathedrals or something. You know, it serves other purposes beyond just doing the science. Anyway, so, and I thought that would be a bit more accessible, because there's certainly many people in the audience who could tell you about, give you much more accurate information about what these are really going to be doing. I'm going to talk about how we got here. So let's start with Newton. You know, it was McRae and Milne wrote a paper in 1935 where they pointed out that Newton could have done pretty much all of cosmology that was known to that day. So this is after GR 1915, after the expanding cosmology 1922 and the final discovery of the expansion. This guy could have done this, but he didn't. But he did think about cosmology, and he did think about gravitational lensing, I think. So this was long after he wrote Principia. He wrote these optics, a trilogy, and he was busy with a lot of other things. And he starts volume 3 with a set of queries, which aren't questions. These are statements. He was just too busy with the Mint or whatever he was running. And so he just stated a bunch of things that he believed in. And the very first one, I think, talks to me about gravitational lensing, about bodies affecting like bending rays, and is this not strongest at the least distance? There's another one, I think it's query 30, where he makes clear that he believes that light is particles. You know, we all know that he was a corpuscular guy. He rejected the wave nature of light. And when he was working, it was well known already to good enough, not to cosmological precision, but to 20% precision, what the speed of light was. So he could have done lensing. And, but as far as we know, he didn't. So it had to wait a little while until these guys, John Mitchell and Laplace, thought about whether light could escape from big stars. So the calculation was, if I consider stars all of the same density, but of progressively larger sizes and masses, there will be a mass at which the escape velocity is equal to the speed that Romer measured, the speed of light. And so light itself wouldn't be able to escape to that. That's not so much, that's sort of strong lensing, if you like, and not so much what we're going to be talking about here. So we have to wait a fair bit longer until people applied Newtonian analysis to light deflection. Cavendish was a very peculiar English gentleman. People would say he was on the spectrum, far out. And many of us have had delicious lunches in the Cavendish canteen, which is named in his honor. And Baron von Sollner on the right, also did this, and this is the plot from them. And so both of them, the back of the envelope calculation is that the transverse kick that a particle will get as it flies past a deflecting mass, right? If you consider a mass coming in, is going to be the acceleration on the order of that accelerating mass divided by the impact parameter spared times how long it stays close to the mass. And if you do the integral properly, you get a factor 2 in here. And then the Newtonian calculation is, well, let's just plug in the speed of light for the speed of the particle, because the mass of the particle doesn't matter here. And what they found was 0.83 arc second. So that was the turn of the 19th century. We have to wait to the start of the 20th century before anything else happens. This must be depressing, even to young people, that new ideas come along so rarely, right? The technology advances with the speed of Moore's law, or it has done throughout, the last 30 years or so. Hopefully it will continue, but actual new ideas, they take on the time scale of a century. I would say we're overdue for one, but don't expect it to come from me. So this is an interesting, funny little twisty bit of the story, because actually Einstein mentions this in 1911, right? And this is where he's thinking about the rocket thought experiment. He's got the concept of general relativity, at least in a germ form. And he says this theory will predict this 0.84 arc second bending, exactly the same as what Newton would have said. Now, there was a measurement, there was an attempt to measure this, right, using an eclipse, looking at stars during the eclipse of the sun, but it was weathered out or failed for some other reason. So they failed to prove him wrong, so he was lucky. And then sometime between 1911 and 1915, by which time general relativity was fully developed, he modified the prediction and pointed out that it was in fact twice that of GR. And then there's this other controversies in here. So the war, there are various things, but I won't emphasize those. He became, pretty much a big public figure overnight once in 1919 when Eddington went off and led the experiment that confirmed this. So it's interesting to ask what was going on. Why did he get the wrong answer and then shift to the right answer? I mean, it's worth looking at whenever Einstein makes a mistake, there's got to be something deep there, right? You know that Landau had a scale of physicists, a logarithmic scale of what physicists, and Newton defines the baseline, right? So he's 0, and Einstein is a half. So Einstein, it's log 10. So Einstein's contributions were 1/3 that of Newton. So really high, because no one else comes even close. He gives his supervisor, Niels Bohr, a 1 on this scale, and he gave himself 2.5 until he got the Nobel Prize, and then he decided to up himself to a 2. Anyway, so if a 0.5 on the Landau scale makes a mistake, you should look at it very carefully, because there's probably, if he screwed up, then there's something subtle there. So at the beginning, he was thinking that general relativity was apparently he was thinking about someone falling off a roof, and that while they were falling to their death, they wouldn't sense gravity. And this, he said, was his happiest thought. So, a bizarre thing. And this is sometimes sort of said into a statement of the equivalence principle, that gravity and acceleration are equivalent. And one thing you can do, so this is a bit unhistorical in that it was really done a little bit later, is to ask yourself, what's the metric of space-time in an accelerated frame? You're not freely falling. Think of a rocket. Here's a rocket. It's being accelerated on the x-axis. And you'll find in various books discussed that you can write the metric of special relativity in no gravity here in this coordinate system, which is tied to the rocket in this way. So it looks like special relativity, except you've got this extra factor here. So in some sense, time is warped in an accelerating frame. So if you send a light signal from the back of the rocket to someone in the front, they'll see it redshifted. A corollary of that is clocks at the front actually run faster than faster at the front of the rocket than at the back. Right, so stop and think about that for a minute. So let's put ourselves in a rocket. We're steadily accelerating. I'm at the back. I take my watch, walk to you at the front, give it to you and walk back. And then a week later, we go and compare clocks again. They're not going to read the same time. They're going to have drifted out of synchrony. And then, so you know, if you buy that equivalence argument, you say, okay, well, we'll replace the acceleration A by the gradient of the gravitational potential if we're in a static gravitational field. And then you can do all sorts of things. You can say that this explains why particles don't just stay at rest if you release them, that they will move up. They want to maximize their proper time. So instead of staying at rest in front of you, if you release a particle, it'll go and fly up and try and spend some time high up where its clock is running faster in order that when it comes back down again, it's maximized its proper time. It predicts the gravitational redshift. And from that, you get the light deflection from this sort of argument. You can say, well, if light gets blue shifted as it comes towards the Earth, then its wavelength must be getting shorter, right? But that means that the waves get bunched up more at the bottom. If you have a beam coming in, a collimated beam, they get bunched up more at the bottom than at the top. And then you can work out, well, what deflection does that cause? And what it gives you is Snell's law, and the same as Newtonian theory, i.e. no factor 2. And that's where Einstein was in 1910, 1911. 5 years later, he's fleshed out and come to terms with the fact that this all worked. You know, it's often said that, or thought that he had to learn a lot of fancy mathematics in that 5 years. It's not true, according to David Kaiser, who's looked over his notes on this. Apparently, he had the concept, but just had these misgivings that it didn't work, that there were all sorts of things, some things wrong with it. And then he had a flash somehow about a year before 1915, when he suddenly realized it did all work. And then he very quickly sent out a bunch, every 2 weeks, he sent out a bunch of notes to his friends, and the rest is sort of history. And what he constructed was Einstein's gravitational field, which is like Newton's in some ways, where the potential gets replaced by the metric, the gradient of that gets replaced by the gradient of that, we call it the connection. There's a tidal field, which is in GR is this ugly 4-index curvature tensor. And then the core thing is Poisson's equation, which relates the mass and the potential gets replaced by Einstein's equation here. And another key thing is how particles drift apart if they're in a tidal field. And that ties down what is this single free parameter in the theory. And it's extremely hard mathematically. And I'm a big fan of Misner, Thorne, and Wheeler. And when they talk about this epoch, they say that the mathematics really wasn't well understood at that time, that you should really think of there being two parts to GR. One is generalized covariance. Einstein's paper had in its title just generalized covariance. And MTW would say, no, that's only part of it. Sure, you can write down the laws of physics in an arbitrary coordinate frame, but that's not gravity. What gravity is curvature, this ugly R thing here, that guy, right? And if that's zero, then there's no gravity. And that's why that accelerated rocket has nothing to do with gravity. The curvature is zero. Anyway, it was hard. Well, it seemed hard, but then people were able to find solutions extremely rapidly. You know, Schwarzschild, who was in the war at the time, got that Schwarzschild solution a year later. But what we're interested in is this, that if you're interested in weak gravitational fields, then you can use the freedom of choice of coordinates in there that's built into this to show that one choice of the metric is this, where that potential phi is just related to the density by usual Poisson's equation. And what you notice is it's different from what you get with just special relativity accelerated frame. There's some monkey business with the spatial part too. So this gives us one way of looking at lensing, which is, I think, the way that most people in cosmology are taught it, that we can look at this metric and go, aha, photons have got to have ds equals 0. So I can look at, if that right-hand side is 0, then I can figure out what's the coordinate speed of light, right? And it's just the square, you know, it's dx by dt. And as if phi is small, then you can simplify this a little here. And so this looks like the refractive index of gravity. So it's just like a block of glass in which the refractive index, it wasn't made very well, and the refractive index varies a little bit from place to place. And once you have that, you can use this. I mentioned Snell's law. Teaching this in France, the students get offended because apparently Descartes did it before Snell. But you can always trump them by saying, no, it was done by Ibn Sal in the year 984. This is how old this science is. And so Snell's law here now tells you that the direction changes with path length with the extra factor 2 in there. So it's an analogy that gravity's just like lumpy glass, but it's different in one way, in two important ways. So if I'm a goldfish in a bowl, right, and light comes in, then the speed of light I measure is going to be lower because it's moving through a medium. Whereas the frequency of the light I measure from a distant source isn't going to change. It's going to be the same. The wavelength will be shorter. And in the case of gravity, the speed anyone actually measures is always c, the physical speed. And but the frequency changes because of the gravitational blue shift or red shift. Either way, it's the wavelength decreasing that goes into computing the light deflection. The other thing that I think most people are not aware of is this factor 2 is also rubbish. It's a gauge artifact. That's a bad thing for anyone who doesn't what a gauge artifact is. So what happens, for instance, if I have this laser pointer and I shine it in this laboratory and look how it curves downward, right? Does it curve down as Newton would have predicted and as Einstein would have predicted in 1911, or does it curve down twice as fast? The answer is that Newton would have been right. This is why Einstein was so tied to that. So there's no factor 2 here. There's another thing you can do is, so I've taught this a lot, and you say, look, you just take the Newtonian theory, calculate what Newton would have got for the deflection of particles, multiply by 2, and you're done. Well, think about something like the Earth and a well, right? And think about an observer maybe at the bottom of that well, looking up at the stars out here. Right? Well, according to Newtonian theory, if you work it through, there's vacuum in here. So Laplacian phi is 0, right? But what that means is there's a non-zero tidal field. If you tossed a bunch of beads up, they would accelerate apart, right? So you think, so light's going to do the same, but just by a factor twice as much. No, there's no effect at all. So these are warnings that you shouldn't take this analogy too seriously. Luckily, it works most of the time. We don't need to change the software to take out the factor 2. So one way to understand the extra factor 2 is that if you were to put a rigid grid in the sun, say, then you would notice that it's spatially curved, right? That if you made that grid out of bars, you wouldn't be able to go to the shop and order a bunch of 1 meter bars, right? You'd have to make some of the bars a little bit larger to make it all fit together. And so there's, if the radius of the sun is here, this is schematically what this two-dimensional surface embedded in 3 dimension has the same curvature as a flat surface through the center of the, say, the equatorial plane of the sun. And so there's this, part of the bending is coming from the equivalence principle, saying that there's a gravitational blue shift, so the light waves get bunched up as they come near the sun. But there's an extra increase of path length because of this curvature, and it turns out to be exactly the same. But it's all gauge dependent. We calculate, we're so used to using this coordinate system, we think it's somehow real, but it's pretty much arbitrary, and it's not what you measure in the lab, and it has various other things. But the reason it doesn't matter is at the end of the day, we want to do some sort of calculation like particle of light leaves the source, goes close to a gravitating system. What happens here is going to depend in an arbitrary way. What the coordinate deflection will depend on my choice of gauge and stuff. But then by the time I get over here, I'm back out in flat space-time, and so everything's kosher. Right. So that's just a sort of summary of that. So with this lumpy glass analogy, you can figure out various things, 3 things. First, the gravitational time delay. It's sometimes called the Shapiro delay. So you take the potential, integrate it along the line of sight. And that's actually what you measure in strong lensing. The time delay, for instance, between flickering of images in a multiply lens quasar. And Blanford and Narayan wrote the most beautiful paper, big long review paper on gravitational lensing that inspired so many people, including myself. It just made me think, even if gravitational lensing is useless, turned out to be useless, it would be so much fun to study it, right? Because they said that, you know, that there's this time delay surface that's central to everything. That's the fundamental concept. And then the light rays are the extremal paths, right, from that. So that's one thing. Second thing is light deflection, right? That you integrate the gradient of the potential along the line of sight, and there's various ways of looking at that. For a single object of size lambda, that's the Hubble constant, this is density contrast, then that's what it looks like. So it's important, big things, goes like lambda squared, so big things have a lot of heft. The cumulative effect is a random walk, and so there's a root n times what you get from one object. And this is, again, I'm quoting directly from one of Roger Blanford's papers very early on, that this was an extremely stimulating way to model things. And we know how to calculate what this is, what scales dominate this. It turns out it's superclusters, things of scales about 30 megaparsecs that are most important for this. Little things aren't very useful. Big things don't affect you because their density contrast is too small. There's a sweet spot where the product of these two things is maximized. And an important number for something we'll get to, I hope, later, is that it's about 10 to the minus 3 in radians, so few minutes. And here's a cartoon I stole from the old LSST website, sort of helping to visualize this process. So we got two things, time delay, light deflection, and then taking another gradient, you get to weak lensing. So you now have a 2x2 image distortion tensor, and it's symmetric, so it's got 3 components. Weak lensing is 3 numbers, but we normally split them into a single magnification, which is the trace of that, changes the size of the object. Sometimes you can't measure the sizes of the objects that are being lensed. So there's a theorem that says the surface brightness of things aren't affected by static lenses. So an unresolved thing, the change in its size because of lensing converts directly to the change in its observed flux density. Right? So that's magnification. And then the other 2 components, sometimes people make this a complex number, it's not important. And this is more interesting. So if you try and use what we know about the way mass is clustered in the universe, so there are galaxies and the galaxies are clustered and so on, then you find that this is something which is about 1% on degree scales, but it gets stronger as you go to smaller scales. And as George Ellis has pointed out very forcefully, this is very dangerous. And as far as we know, it could well diverge, right? Well, the measurements just say it's growing up roughly inversely with angular scale. And we'll come to the interesting things that would happen if it were to become 100%. So what are some applications of these things? There are lots of them. Microlensing, I always think of it as being, it was really promoted by Bohdan Pajinski, no longer with us, sadly. I think of it as a subject that was just too successful for its own good, right? When they started, it was a real open question, right? We know it was known at that time there was dark matter in galaxy halos, lots of dark matter in clusters of galaxies. Well, perhaps it was MACHOs, massive astrophysical complex halo objects. And Bohdan said, we can test this, because if it is, we just monitor the the bar of the Milky Way or the Magellanic Clouds. And if we look at 1 million stars, we'll see every now and then, we'll see one of them undergo a microlensing event. We have people here who are now doing this with Subaru and stuff. And they put themselves out of business because they basically ruled out most of the parameter space. I think there's a tiny little window at about 30 solar masses. Then there's strong lensing. I'm probably going to skip over this because I spent too long talking about the old history. But maybe I'll just flash up the slide briefly. And then I'll tell you how weak lensing got started. Which leads us to the present day. And then in the final part, I'm going to talk about some stuff which is near and dear to my heart, which is another long historical story going back 50 years. But this one has a happy ending, I think. So time delays, strong lenses. It was Fritz Zwicky was the, so Einstein thought about lensing by stars. That's hard to measure, measured for the sun, but otherwise a bit tricky. Zwicky was first to point out that galaxies would be much better. And that if you have a situation like this, where there's a source, a point source, ideally, a lens not far from the line lens galaxy, then you'll see multiple images. And I was a student in 1979 when the first one of these was discovered. And so this went from being a subject with no applications, there was an infinite increase in applications. And so you could figure out something about the mass distribution in the lens, and it was Refstel who pointed out that this is a way to get the Hubble constant, and we heard a talk earlier, or was it yesterday, on modern attempts to improve that. Let's turn now to weak lensing. A lot of this was foreseen by the Soviet cosmologist Yakov Zeldovich in a pioneering paper in 1963. Rachel Webster proposed that we could tell there was lensing going on in the universe because what it would do is change the shapes of distant galaxies, and that the more distant ones would be more elliptical. But she wasn't thinking about the shear as a sort of two-component vector. Right? So it's a little bit different from what we do today. And around the mid-80s, two techniques emerged which should have measured the same thing, but actually gave different results, was for the dark matter distribution around galaxies. And one of these was quasar-galaxy associations, and the other is galaxy-galaxy lensing. So this quasar-galaxy associations started off as being a fringe thing, because quasars were supposed to be super distant, the galaxies were not, but the Barnothes and people claimed that there were an uncomfortable number of cases where the quasars were close to a foreground galaxy, and they were considered to be cranks, I think. And then lensing took off, and it was realized that effect should be there. And it's galaxy-galaxy lensing. It's a little bit subtle. Again, Ramesh Narayan led the way on this, pointing out that you might think, okay, if you look through the halo of a galaxy at a distant quasar, it'll be made brighter. Well, that's true, but they're made brighter by being made bigger, and by being made bigger, they get to be less numerous on the sky. And so what you find is that for faint things, you will actually see fewer background quasars. You won't see associations. It's only at the bright end of the quasar luminosity function that there'll be this enhancement. And the weird thing is, well, then people went off and tried to measure it, and the samples sort of already existed, and found it, but it was much too large. So I think it was some, today people blind their analyses. Maybe they should have blinded it back then. Because I think this was a confirmation bias. The theorists were saying you should see this, and lo and behold, it was seen. And as far as I can tell, there's this paper here that claims that you still get too large an effect. So maybe it's worth looking at. But coming closer to what we've been talking about a lot at this meeting was something that Tony Tyson, who was at Bell Labs, developed. CCD detectors had only just come along. They arrived in the 70s and they were very small. They rapidly got bigger, and so you could use them usefully for astronomy. And Tony realized he could get time on the CFHT and take tons of images of the same field and stack them up in the computer. So big data, certainly a big data project at the time. And so we're talking about, close to 100,000 galaxies here. And so the next slide shows some of the results. So they had a bunch of fields scattered around the sky in this manner, and they measured an average shear for each field, looking to see if there was any what we would call cosmic shear nowadays. And they got a null result. But you shouldn't knock it, right? At this time, 1983, our understanding of how strong large-scale structure was very different from what it is now. There was something called the Rubin-Ford effect, and there's Vera, who you all know for having found dark matter around halos. She did something else, which she did a clever thing to show that there was a shell of galaxies around us, very large, that she measured our motion towards it and found that it didn't agree with the CMB dipole. So it seemed there was very large mass fluctuations on large scales. So this null result here was not at all a foregone conclusion. It was an important result. The other thing they did was, this is their galaxy-galaxy lensing, where the prediction, depending on where you put the outer size of the halos, was either like this or this, and it should really be more like this. And what they saw was, again, a very weak effect. So this was completely the opposite from what the quasar-galaxy association seemed to be telling us. But then the third thing they did really set the ball rolling, because they applied this to clusters of galaxies, which are more potent lenses. So for the non-astronomers in the audience, here's a beautiful cluster showing actually some strong lenses there. And these fuzzy things are the elliptical galaxies in the cluster, and all these other things are background galaxies. And what Tony did was sat on Abel 1689, which is a poster child for weak lensing, stacked up the images, tried to separate out the blue images from the, well, he made a very blue weighted image, which emphasizes the background objects. And you can see that they're not, that they're showing this tangential alignment. And then he made this garish thing here, which was what? Right? It was the signal processed in some way. What was it? Was it the potential? Was it the surface density? No one had a clue, right? And this is science emerging from the fog, right? The fog is lifting, and you know, so many people, myself included, thought this is good, because what you have here is a signal which falls off roughly inversely with distance from the center. But the number of background galaxies, which sets your noise level, was going up like distance squared. So square root of n was going up like r. So if you could measure it at 1 megaparsec, you can measure it at 10 megaparsecs. But even better, once you get to 10 megaparsecs, you're not dealing with a single cluster. You've got this supercluster, the next one, you've got 100 superclusters along the line of sight. And so you get a root 100 boost there. So this was bingo. We can do cosmology. And whatever this is measuring, it's a measure of the total mass, right? There were various ways of measuring the mass. You could look at the velocity dispersions, then you were messed up because you didn't know the orbital anisotropies. You could look at the X-ray temperatures, that only told you about the inner parts, and maybe there were magnetic fields and stuff like that. This was a direct, beautiful, clean measurement of the total mass distribution, primarily dark matter, but everything. And so I think this was just to remind me to say all those things I just said. Well, what was it measuring? The other thing was, why were they getting these other null results? That turned out to be a calibration thing, that the effect of seeing was much more important than was initially anticipated. So there was a lot of activity in the next few years. And so that's been used to, started off, the game was mapping out the dark matter. Then it became more looking at how the dark matter's clustering is evolving with time, because that tells us about dark energy. And the other thing that I think is super cool and important is things like this is the bullet cluster measurement, where you see three things. You see two clusters with their galaxies in white there and there. You see X-ray gas here, which makes it appear that this is two clusters that collided and the galaxies passed through and the gas didn't. It shocked, whoops. And the blue is the dark matter. So it's telling you that dark matter behaves like galaxies and doesn't behave like gas, i.e. the dark matter's non-interacting. You get strong limits on the self-interaction. And here's some of the state of the art of this. Here's a colleague of mine who was at DES when he made this slide for me. And this is the future, is going to take this to 15,000 square degrees over the sky compared to this much smaller region here, and with much better image quality. So I'm going to tell you about the second part, is a slightly different application of lensing, that even the weak lenses here probably don't know that much about this. So here's the CMB map of the sky from Planck, and there's these ripples on the face of God, and we know where they come from. They correspond to the sound horizon scale at last scattering, and the angular scale tells us an important thing, which is that the universe is very close to being spatially flat. Depends on some other things as well, but it depends super strongly on the spatial geometry of the universe. So we know that after that, we know that we're in this sort of Goldilocks case here, where we're not in a negatively curved or positively curved universe. Another thing, the other foundation of the lambda CDM model is the lambda in it, which is also coming from if the universe is flat, you needed something else in addition to the matter, and lambda would do the job. The other thing is the Hubble diagram for supernovae. But both of these assume that we live in a universe with no structure affecting, no gravitational structure along the line of sight to these distant supernovae and the CMB, which we know to be false. There is structure in the universe. So the question is, does that, are these measurements biased in some way by the structure? The extreme version of this is what's called back reaction. Strong back reaction is the suggestion that the effect of the structure in the universe is so strong that we've been misled into believing that there is dark energy, right? few people push that anymore. But the idea that now we're in the 1% precision cosmology domain, even small effects could be important. So let's be clear about what we're talking about. In cosmology, there's just too many damn distances, right? You know, locally, you can measure things with parallaxes. Then there's redshift, which is a sort of measure of distance. Then we've got this pesky conformal distance that appears in the metric, right? We've got something else. Cosmologists never use this. I don't know why. If they're scared of it. The affine distance. We're not interested in any of those. There's these two other distances. One is the angular diameter distance, is dA, which is a function of redshift, and the luminosity distance, similar. And both of these depend on the cosmological parameters. And they answer the question, right? If I look at an object that I know is a megaparsec big, and I see it at a certain angle, how far away would it have to be in an empty universe to have that size, angle size relation, right? And then there's luminosity distance is similar. So these are the flat space formulae, if you like. And so these are apparent distances that you apply to either standard candles, things where you think you know how intrinsically bright they are, or measuring rods, which like the BAO. So these are and everyone would agree that lensing changes these distances. So if you look through an overdense region, then things will be magnified. And so they'll look closer. Right? They'll be bigger and brighter. And so these dA and dL become random functions of direction. That's not what we're talking about. The question is, does structure actually bias the mean as well as introducing a scatter? Because if it does, we'll have got the wrong cosmological parameters. And this goes back to Jakub Zeldovich, who you should really read this paper. It's wonderful. You can tell that he's constructing cosmology in his own idiomatic way. He doesn't even mention redshift. He uses this weird thing, red delta, which is replaces redshift. And what he was thinking about, he was the first to do this, was say, well, we have these distances we calculate, assuming falsely the universe is homogeneous, there's no structure. But what if I looked at a galaxy along an empty line of sight, and he has these cone diagrams? This is the focusing of light by the mean matter density, and here's where you look along an empty beam. So everyone calls this the Zeldovich empty beam paper, right? And he works out that things will look fainter. Let me rapidly move on through. Oh, by the way, the information content in his pictures, this is in his paper too. I think they're the same as this, but they were just, 50 years earlier. At about the same time, Feynman gave a seminar at Caltech on this. He didn't bother to write it up, but Jim Gunn, who we know and love, did a few years later. And I often wonder, was there any communication across through the Cold War between Zeldovich in Moscow and Feynman in Caltech? I bet there was. And a bunch of other people did it. I won't go into any details. Ron Kantowski, Charles Roeder. It became clearest, I think, with some papers by Peter Schneider, who's a towering pioneer in the field of gravitational lensing. And the most important thing for us is he crystallized the focus on the focusing, what they called the focusing theorem. And interestingly, this concluded that things viewed through clumpiness are further than they appear, i.e. they appear nearer, so they're brighter. This is the opposite of what everyone had included before. And I haven't mentioned Weinberg yet, we'll come to that. Right, so here's the people he worked with, Stella Zeitz and Jürgen Ehlers. It was his supervisor and he was Stella's supervisor and husband. And this is their statement. It's rather German and sort of loyally in the way they state it, that it's there. And it has to do with this, that, oops, yeah. So you're interested in, I'm looking out at the universe, so I think of a bundle of rays coming out of my eye or telescope, going back across the universe, and there's some cross-sectional area A, right? Take the square root of A and call that the distance, then the second derivative of the distance along the line of sight is equal to this thing here times d. And r is a measure of how much mass there is in the beam, and sigma squared is something else, but it's the square of something, so it's positive. That's the theorem, that ordinary matter has a positive r density, and I'll explain what this is in a second. And so that this total thing is negative. That says that light rays are always being focused, either because there's mass in the beam or because of sigma squared. Where does this come from? It comes from GR 101, right? Where you say you use the definition of curvature to compute something called the geodesic equation, and then that gives you how two parallel rays diverge from each other. And then what you do is you apply this to this bundle of rays. You take a guiding center and you look at how the neighboring rays are moving away from it. And you do things like define theta to be d dot over d. There's basically, you can imagine here that there's some observers who don't see any flux of radiation in the transverse direction. They have define a velocity field, and that velocity field's got an expansion rate, theta, and it's also got a shear, little sigma here, and omega is the vorticity. And that big sigma squared was the same as sigma squared here. All right, now, there's other equations here too. This has a local flavor to it because this is the Raychauhuri's equations, which are the basis for the singularity theorems of Hawking and Penrose, but here being used in a slightly different way as a basis for gravitational lensing. And so that's what, so this sigma squared is a little bit weird. I've got too much material here. But these are, in the interest of being historical, there's a lot of rays involved in this, because you're thinking about a bundle of rays. And you've got Raychauhuri, whose name I'm mangling, but apparently Indians pronounce his name differently, so I can pronounce it how I want, I think. And then a lot of this is due to a brilliant guy, Ray Sachs, who was, I forget where it was, MIT or Caltech. Right? And what it looks like, that equation we had up before, was like the cosmological acceleration equation. This is where the singularity theorems come in, and that if you've got a positive pressure, then you're guaranteed to have a singularity at the beginning of the universe. Well, here, the thing that's playing the role of pressure is not pressure at all. It's this sigma squared, which is the shear squared. All we care about is that it's positive, but we're probably interested, what is it? So we have shear in cosmology, which is the ellipticity of that beam. And what the general relativists define shear as is how fast that ellipticity is changing. So it's like gamma dots. And Giant Narlikar, who was at IUCAA, really emphasized this very strongly, that this equation is so powerful because it directly relates to the matter density in the universe. So remember the lumpy glass analogy. We worked with the metric and calculated how light rays moved according to some metric. Here, there's no metric. Here, you directly take the matter, the Ricci tensor R, right, tells you directly how the light gets focused. You don't have to solve the Einstein's equation to go from how the matter produces a metric and then calculate how the light rays propagate in that metric. It's much more direct. The other thing is, everything in this equation is physical, right? There's no core. What we did before in the lumpy glass analogy had this awful, really ugly gauge dependence that we were calculating coordinate speed of light and things like that. These are not real things, right? These guys are doing it in a much more honest way. But they reach a pretty strange conclusion. So it went up and down what they were predicting, but it was always non-zero. And then in 76, this guy came along and pulled the rug out and said, sorry, guys, there isn't any effect at all. Right? That gravitational deflection by the clumps will produce the same average effect as if the mass were spread out homogeneously. So this has been a debate, right? There's a conflict here between someone who has pretty high standing and a whole bunch of other people who have equally high standing in their respective fields. And it burbled around for a long time. This was all done back in the 70s, 80s. And it resurfaced in 2014 with this back reaction stuff and people doing perturbation theory to try and figure out how light would be propagated. And it was all very complicated. Equations that covered an entire page of the APJ, you wouldn't believe it. But it all got condensed down to this rather simple, one of the results is this rather simple formula. The change in brightness of things is going like kappa, that's the RMS surface density squared. This is what George Ellis had been warning about, that if you go to small scales where this variance could be diverging, it could become infinite as far as we know. And what they also did, I think, was kind of suggest an explanation for what might resolve the conflict. So what's this football over here? So this guy has this beautiful argument. What you want to know is, if I look at a whole bunch of sources at redshift 1, say, and I'm looking through this lumpy medium, will they look brighter than if I were looking through a uniform medium? He turns it around and he says that's the same as asking, put one source at the center of the universe and imagine an ensemble of observers on the sphere who all see that source to have redshift 1. And here's now you can see the answer coming, I think, that photons can get deflected, they can run, but they can't hide. If that source is emitting 1,000 photons a second, then there's got to be 1,000 photons per redshifted second passing through that sphere. So maybe this guy sees the thing to be brighter, and this one sees it to be denser, fine, fainter, that's fine. But on average, it's got to cancel out. Well, these guys are suggesting that that whole picture of this spherical surface is wrong. They're saying lensing is going to make that sphere crumpled, and that'll change its area. And there's, how much time do I have? Minus how many minutes? So there's one objection to this was raised by George Ellis. I'll skip over it. Ask me about it. What these relativists doing perturbation theory were thinking about is this. Here's a crumpled surface or a wrinkled surface. Evidently, the area of that is not going to be the same as a sphere of the same size. So what is the change in two order of magnitude in the area? Well, so with John Peacock, we set out to calculate this. And this is the setup. You say, here is the surface, say, of constant redshift. And I'm looking through a region where there's some structure. I'm going to limit it to that region. And then I can calculate things like, what'll be the change in the brightness of objects here. So there's actually two effects. So one is that wiggly lines don't get as far as straight lines. Right? When you're drunk, it takes you've got to go further to get home. And the other thing is that what was pointed out was that wrinkly surfaces have a higher area. Well, it turns out these two effects we showed are of the same order, but they're both very small. And I won't bore you with the calculation, but you can sort of see it from this. Here's another wrinkly surface, right? A swimming pool with little waves on it. Right? So what's the fractional change in the surface area introduced by those waves? Well, I think it's reasonable to say it's got to be quadratic in the amplitude of the waves. Right? It ought to be the square of something. And it's a dimensionless number. It's a ratio. Right? The only thing you've got is the mean gradient of those waves. So to order of magnitude, maybe there's a 2 pi, who cares? It's going to be like if the gradient, which is a dimensionless thing, is 10 to the minus 3, then it's going to be 10 to the minus 6. And that's exactly what it is in cosmology. And so it's not big enough to worry about, and it's not what was being calculated. Here's the details. We get this beautiful or ugly formula for what's going on. So what is causing this? None of the calculations here is wrong. It's all in the interpretation of what these calculations mean. And it's actually Tom Kibble and Richard Liu who gave the first hint of what the answer is, because they noticed something interesting, that Weinberg's argument says that the mean amplification is 1 for sources. If you average over sources, the mean amplification is unit. There isn't any amplification, right? The amplification factor averages to 1. They said, well, what if you, instead of averaging over sources, you look in a certain direction and measure how bright a source you find over there is, and then do it in other directions and average over directions. They found that it's not the magnification that averages to 1. In that case, it's the inverse magnification. And this seemed interesting to some people, but no one paid any attention to it. So the inverse magnification averages 1. And so you might think, oh yeah, that's more relevant if I'm looking at the CMB. I'm not looking at sources, right? I'm just pointing my telescope where I want to point and look at whatever I find at the end of the beam. And this is supposed to try and explain why there would be that kind of effect. To think of this toy model where you're the observer at the center, And there's a shell of lenses around you, either voids or overdensities. And the overdensities focus the light, and the underdensities defocus the light rays. And so you can see, you're going to see more sources through the underdense regions. If you look at the density through which you see a source, it's biased low. And that's essentially it. Right? That explains these differences. So what were people calculating? Were they the reason this introduces a bias is because the average of, if mu averages to 1, the average of 1 over mu, if mu is fluctuating, doesn't average to 1, right? Averaging and taking nonlinear functions do not commute, sorry. They do compute if you write a Perl script, because the Perl script's happy to give you the wrong answer. So what were people working with? They were working with square root A. And that they should have been working with A. Right? And that's what their calculation correctly gave the bias in that nonlinear function. So this is what we pointed out in the paper. Everything hangs together. And if you say, well, why did they work with square root A? It turns out it's really convenient mathematically to do that. But it's not actually, you're not posing the question to which you really want the answer. So we would say, with great apologies to Giant Nalekar, who we really respect, that this extra term in here isn't really a tendency for light rays to be focused. It's got nothing to do with general relativity and subtle effects that ordinary mortals like you and I can't understand. It's a simple statistic effect. So sorry I went on far too long, but the first part was the history from Newton via Einstein to Euclid, LSST, and SKA, and let's hope Euclid doesn't blow up on the launch pad and LSST works as fine. And the second part was this 50-year-old problem that had been bugging a very small number of people, myself included, and who was right, Weinberg or all the GR people? And we side with Weinberg, basically. So thank you for your time.
Okay, so if there are questions.
You mentioned George Ellis had argument against what Weinberg was saying. So what was that?
Yeah, thank you. I skipped over that slide. So it's that he has this beautiful picture, which is clear to him. This is our past light cone in a lumpy universe. I like it because I think it's beautiful. I wish I had an artist who could make pictures like this. But we made this picture here. So this is the essence of George's argument. Imagine a universe in which there's lots of little lenses. We don't know that's not the case, right? What a lens over here to the left, if I've got a source way over there, these light rays coming from it, a lens here, say, then they get deflected, acoustic forms, and the surface of redshift 1 gets folded over on itself, right? And an observer sitting here sees one image of that source over there, and an observer sitting here sees 3 images. And that's increased the area. That's a real strong violation of what Weinberg was assuming. Now, we don't think that's a valid objection. It would be if you resolve the multiple images of supernovae being microlens, but we don't. So if you only have the agglomerated flux density, you don't care. That's George doesn't buy this, I have to say. That worries me greatly. But ask him why I'm wrong.
Just follow up. So if dark matter were a bunch of black holes, this would make sense?
Yeah, well, yeah, certainly. But even it doesn't have to be black holes, right? In a hierarchical picture, you know, probably not lambda CDM, but yeah, something with stronger small scale. There's something else, though, is that these distances become random functions of position. And that is what drives the bias, which is very small or, you know, or not. But we sort of know what that fluctuation is. People like the CFHT legacy survey people have a term in their modeling which allows for the scatter in luminosity, in intrinsic luminosity to increase with redshift, and it's not large. So there's no indication empirically that things are blowing up badly. People want tea.
Does the acceleration of the universe affect any of these, or in the future would? I mean, since it's you would think that it should. This is sort of probably more with the universe which has without a cosmological constant in some sense.
Well, this is all done in, I'm assuming lambda, you know, we can't get away from it. But whether lambda, whether a cosmological constant affects lensing is another big debate that might be a storm in a teacup. But again, there's a small community who've been debating this. And let me see who it is. It's, so certainly John Peacock. So cosmologists in general are of the way they think about things is there's a background cosmology with lambda and stuff and a mean density. And then there's fluctuations, and it's the fluctuations that cause lensing, right? And so to them, lambda is part of the background. So it doesn't come in. But the relativists, oh, I really wish I could remember the name. They come to a different conclusion. And it's two communities separated by a different language. They refuse to come together and talk in the same terms. Right? And it's like I was saying, the only distance that relativists will ever want to talk about is affine distance. And cosmologists, 95% of card-carrying cosmologists don't even know what it is. So it needs to get resolved. And
what is the tension there?
The tension is whether we're interpreting strong gravitational lensing, right? Whether we should allow for lambda on deflecting light going through. There's a really interesting sort of, there's a bit of a paradox, which is what happens if you're just out in the empty universe? There are voids in the universe. Imagine yourself at the center of one. And all there is the cosmological constant. There's one argument that says if you have, say, a photographic plate and shine some beams of light through it, you'll measure them diverging. And there's another argument, equally strong, based on Raychauhuri's equation, that says they don't diverge. And I honestly don't know the answer. There are these super subtle things. But there's no end of people who want to say the cosmologists like to do linear theory calculations and they're throwing the baby out with the bathwater. And they need to do the calculations more carefully. And when they do, they'll see these extra effects. But so far, they haven't, that assertion has not been proved correct.
Any other questions? Well, then let's thank Nick once again, and
Thank you.
we'll have tea outside. So.